Okay, so we're going to continue on in our handout. Remember, this is our practice problems for Module 4. So if you don't have the printout, then you're required to write it all out just as you're seeing it here, even the sections that are like fill in the blanks and such. So hopefully you have the ability to print it out because it's just a little bit easier. So we don't need to hand this in until we're all the way through the handout. So between today and the next time that we get together, which will be Wednesday, then we should be, through this, and then that'll be when you hand in your practice problems for Module 4. So as we look here, section 4.5 in our book, this is going to be on page, yep, it is on page 70. And it starts this section right here. So in the problems above here, these are kind of like problems that were for the section previous. So now we're looking at a new section here. This is called resultant of parallel forces. Okay. And this is exactly what it sounds like. We're going to be looking at forces that have the same, if you would, line of action, but they never intersect. Okay. Which means that if they never intersect, they are going to be parallel. Okay. So what we want to do is we want to find the resultant when we have these forces that are parallel, but don't share the same point. So as we look here, we know that resultant R of a parallel force system must have the same equivalent effect on the body as the original system of individual forces. Now, just like we have been doing up until this point, we've been talking about resultant. Resultant, as we know, is the one force that's going to replace, multiple forces and have the same net effect on the body. Same thing here. But because we are not sharing the same point, because these are non-concurrent force systems, now we have to figure out, well, where would that be located? So we not only need the magnitude of the force and its direction, but now where does it have to be located along the body to have the same net effect? Okay. So we're going to be finding a distance here. So we have a little bit of an equation, or a couple equations that we have to keep in mind. And these are found on actually page 70, not 71. And they're right down here. Okay, right down here. So what I want you to do is I want you to write these out. And that way they're available to you in that section right here on page 11. So for instance, we're going to have some of the forces, and I'm going to add X and then do a Y, is going to be equal to the resultant X component, okay? If it's in the X direction, like horizontally, all right? And then that's going to be equal to plus or minus F1, plus or minus F2, plus or minus F3, and so on, okay? So however many there are, we are going to add those, and that's going to give us our resultant, if you would, X component. If we have forces going in the Y direction, okay? Same thing, sum the forces in the Y, that's gonna give us a resultant Y. And then that's going to be equal to sum of forces 1 plus or minus sum of the forces 2, or I mean some plus or minus force 3, and so on, however many forces there might be in that direction. Okay. And that takes care of really two versions, if you would, of the sum of the forces equation here. They just put it as generic sum of the forces, but I want us to remember that we're going to be seeing them either horizontally or vertically, okay? Or. Then we've got our next equation here is sum of the moments, okay? So as we know, when we define a moment, we have to sum around a point. So the point that they're kind of showing here is like an origin or a zero, or we would have a point A, a B, a C, whatever it might be. And we were doing that earlier in this module. Now, we know that moments are equal to a force times its perpendicular distance. So if we look here, you're going to notice that they're calling this distance R, kind of like a radius from the point, if you would, okay? So they're calling it F1 times R1. So it would be its corresponding distance, okay? So we would have, for instance, F1 times R, and I'm gonna actually give myself a little bit of room here, sorry. I'm gonna put them in parentheses, F1 times R1, and then we're gonna put a plus or minus out front, depending on the direction of rotation that we end up seeing with that force offset from the point that we're identifying, okay? And then we're going to have plus or minus F2 times R2, or distance 2. And remember, these are all perpendicular distances from the point that we're summing around. And then another plus or minus F3 times R3, and then so on, okay? And however many forces would apply for the offset, for the moment that we're trying to generate or find. Now, once we sum these all here, we can also say that some of the moments around that point, once we add these all together, that's also equal to the resultant times its distance away. So we call that R bar. So it's like the average distance that we need, or the position of that resultant to that point. Okay, so this is the distance away. And then that's the force, okay? So R is the force. Something I've been noticing on homework that's been handed in. I know I told you can call forces whatever variables you want, but I want you to know that reserved for resultant. So when we're asked to solve for a resultant, don't use R for any other variables except that final one, okay? Kind of reserve that for that because it is pretty specific. Now, when we find the total moment, okay, then we have this equation right here. And this one becomes really important because then what we can do is you'll notice that we can solve for the distance that resultant is going to be by rearranging that equation. So we can say, all right, solving for R bar, we can say that's going to be equal to the sum of the moments around that point divided by the resultant, okay? And now if that's in the X or Y, that's simply adding up those forces in that direction, okay? So we're gonna be doing a couple examples here that are gonna use this information. So we just kind of got it in place, all right? And I know it might not make a whole lot of sense right now, like what are we gonna use this for? But the next examples will help us with that. Now, there is a statement down here. It says the goal of these problems, when we work them to find the result of a parallel force system, is to determine what the resultant force is magnitude-wise. Oh, hi, Tom. Do you need me? Oh, okay. Hi.
Hi, you'll see me someday.
Yeah, do you guys know Tom? Have you had him before in class? Yeah, some of you have, absolutely.
Thank you. Oh,
Yes.
good. Good to see you still.
Thanks for stopping.
Sorry.
No problem. Okay, so the goal of these problems is to determine the resultant force, so magnitude and direction. And that just means up, down, left, right, whatever it might be along the axis that we're looking at, okay? And then you'll notice, and to place it, and that's going to be our R bar, okay? The lowercase r, and that is going to place it in the place where it has the same net effect on the body as all these separate forces did at their separate locations. If we turn the page here, okay, this kind of gives us an idea of, like, if you would, a before and an after. So if we look at figure 4.9 at the top here, and I'm not crazy that they put it at an angle, so you can imagine it just being vertical or horizontal. But we've got three forces. Notice that they're parallel. They're never going to intersect, so we can't do a concurrent force system with this. So we have to find the resultant using our moment equation. So here's our O, our origin. Here are these offset distances, R1, R2, R3. They're the perpendicular distances to each one of the corresponding forces. So what we have here is we have a force system of three individual forces at offset distances. What we want to do is we want to find out what's the effect that those three separate forces have on the body. That's when we sum our moments around O and take our F1 times R1, our F2 times R2, our F3 times R3, okay? And once we do that, we determine what its effect is on the body. Now we're going to find what is that resultant, okay? What is the one force that would replace all three of these, okay? And then not only what it is or what its magnitude is, but where does it need to be located to have this same effect on the body? Okay, does that make sense, everybody? And that's where when we find, see, let me go back to this one. When we find the total moment with those individual forces at their individual distances, that's going to be this number right here. We're going to know what the overall resultant is because we're going to be summing our forces in whatever direction they're in. And then now we just rearrange this equation to solve for R bar. Where is it located? Okay. So, so that's really the process that we're going to be going through, or that's the goal of what we're going to be going through. So down here, there is a little bit of a process. It says, number one, we're going to draw our free body diagram in our convention. Okay. That's going to be number one on all of our problems. Then we're going to determine the resultant by summing the forces in the direction that they are found. That's where, are they vertical? Are they horizontal? So it'll be one of these two equations because they're parallel force systems. So we're not going to be using we're not going to be using both at the same time for these, okay? Then we want to determine what the moment is that's generated by the original individual forces and their offset distances, okay? Then we want to determine the placement of R bar. And then we want to draw a final diagram. It lets me know that the numbers that you just calculated. So for instance, in some of those problems in module 2 and 3, if you're calculating for some forces, I want to be able to see, and I want you to let me know that you understand what you just solved for. So that's why I always like this diagram at the end. Okay. All right. So let's look at our problem. The problem we're going to do is on page 71. It's example 4.4. Okay. And if we turn the page to page 12 in our handout, then this is where we're going to be starting here. But let's look at what we have here. It says for the parallel force system acting on the rod in figure 410A. So this is like the initial illustration. Okay. Don't mind these two. Determine the resultant of this force system. So there's three forces here. We have one at A going down, 10 kilonewtons. We have one at B going up, 12 kilonewtons. And we have one at C going down, 25 kilonewtons. Okay. We want to know, first of all, what is the resultant? What is the one force that would replace all the three of those? And then where is it located to have the same net effect on the body as those three separate forces? Okay. So we'll get here. All right. And there. So, so let's go through here. And what we're going to do is we're going to draw our free body diagram and our convention. All right. Always draw a free body diagram and add our convention. So I do that before we do anything else. So you'll notice here that we have going up and to the right is positive, as well as counterclockwise rotations. Remember, we've now added moments to our convention. And then now we're just simply going to draw a horizontal line, simplified version of, that's what a free body diagram is. So we're not going to draw the thickness of our beam. We're just going to draw it as a line. And we have an A, we have a B, and we have a C. There's 4 meters between the A and the B, and there's 6 meters between the A or the B and the C. So it's B is a little bit closer to A. This is C, and is B, I forget, it's going up. So this, I'm going to put B here. So this is 4 meters. This is 6 meters. I have a force going down at A. And that is 10 kilonewtons. So this is, we'll call it F1 is equal to 10 kilonewtons. Use the variables that they have here. Then at B, we have one going up. Okay. And that is 12 kilonewtons F2 going up. Okay. And then at F3, down again, 25 kilonewtons at C. So the first things first, we're going to find the magnitude of the resultant. And this is not hard to do. You can see that we've got three forces. They're all in the vertical direction. Okay. Some are going up, or one is going up, two are going down. So what we're going to do is we're going to sum our forces in the Y direction to get our resultant value. So we are going to sum our forces in the Y direction, and this is going to give us our resultant. You could call it the resultant Y if you want, but it's only in one direction, so it's going to be the resultant. So I'm going to leave it as the resultant, okay? So then I'm going to say, all right, directly down below on the sum of the forces in the Y side. Oh, something I've been noting that as you've been doing, for instance, rectangular component method, anytime that you have to sum your forces in the X or the Y, make sure you're always telling me what you're doing first and then put the numbers down. If you start writing numbers, I don't know what you're doing. And then it's all of a sudden a final answer and you've got a variable. And I'm like, how do we get there? So this is letting me know what you're going to be doing. So on the left-hand side here, I'm going to sum my forces. So I'm going to look, I'm going to work left to right. I've got a negative 10 kilonewtons. Negative because it's going down. I've got a positive 12 kilonewtons because it's going up. And then I've got a negative 25 kilonewtons because it's going down. And now that's the left-hand side of my equation that exhausts all the forces that are present. So now I'm going to set this equal to my resultant. And again, you could call it resultant in the Y, but it's only going to be in one direction. So now I can add and subtract. So it looks like I have a negative 35 plus 12. What do I end up with here? It's going to be minus something. 23. Anybody else get that number? That sounds correct. Right, we can even look in the example. I have it down underneath. Keep the negative here, okay? And it'll make a little bit more sense why. This gives us the direction of the resultant, okay? The direction of the resultant. Now, the next step, let's kind of look back at our process and see where we're at. On the previous page, remember, we had our little process here. We did our free body diagram with our convention. We determined the resultant by summing the forces in the direction that they're found, okay? Now we want to determine the moment generated by the original forces on the beam, okay? So you'll notice here, step number 3 says, determine the moment generated by those original or those individual forces on the beam. So we're going to go up here and we have to decide now where we're going to sum our forces around, okay? Or I'm sorry, sum our moments around. We want to use one of the points that are on here, all right? Whether you use A, B, or C really doesn't make a difference. I tend to, if it's not defined for me, I tend to just start with the left-hand side, kind of where I'm starting to read, and that's where I'm going to go. So that's what I'm going to do. I'm going to start by summing my moment around point A. So again, you have to tell me what you're going to do by putting the summation symbol, capital M, and A is going to be the letter that I'm summing around. So summation of the moments around A. So that means I'm going to put my finger on A. And what it also means is that F1 is eliminated because it's going through point A. There is no offset distance. Remember, moments are offset forces causing rotation. That's not going to be included. So the first force that's going to cause rotation is going to be the one about B. So that means that, oh, I'm sorry. I'm going to get my equal sign. And I'm going to find the total moment. So this is going to be 12 kilonewtons times, and my perpendicular distance is 4 meters to B. Okay. And then as I go back up here, I got to put a sign out front. It's going to go in a positive direction because my convention says counterclockwise is positive. So I'm going to put a positive out front here. Okay. Then I'm going to go to my next force that's offset with my finger on A. If I pull in the direction of F3, it is going to rotate clockwise. So the moment is going to be the 25 kilonewtons times. Now from A, the total distance is 10 meters to the perpendicular distance. Okay. And if I rotate in the direction of that force, we're going to have a negative out front. Okay. That exhausts all the forces that are offset that would cause rotation. So there's only 2 of them here. So now we want to multiply, add, and subtract here. And we're going to get a total moment about point A. You guys get 202, negative 202. Okay. So hold the sign, okay? Negative 202. And what are our units going to be here? Kilonewtons times meters. Absolutely. Kilonewton meters. Okay. Make sure you have your units in the top here, but then also we can see that they multiply together, they combine, And our final units will have, or our final answer will have the same units on them. Okay. So now what this told us was we looked at the individual forces, and when we sum our moment around A, the tendency of those two forces located where they're at is we're going to have a negative moment of 202 kilonewton meters. That means that when I'm at A, this is going to want to go in a clockwise direction because of the negative value here. Make sense to everybody? Okay. Now, we want to find out where can we put the one force, the resultant, and still have this same net effect on that beam, okay? So if we turn the page, the next step that we have here is we're going to determine the placement of R bar, okay, of the resultant. So if we go back to the page before on our workbook, we are going to use this equation now, okay? This equation. So we want to solve for R bar, and all that was a rearrangement of above here, the resultant force times its perpendicular distance R bar. But now solving for R bar, we're going to use that for an example. So R bar is equal to the summation of our moments. Now we summed moments around point A in this problem, divided by our resultant, okay? You have to write this out for me. This is writing the equation in variable form. It's telling me what you're going to do before you do it. Don't just start putting R bar in numbers, okay? Tell me what you're going to do first. So now I'm going to put in my values. I'm going to go back a step, and I know that some of my moments around A were a negative 202 kilonewton meters. So I'm going to write that on the top here, a negative 202 kilonewton meters, divided by my resultant. Okay, my resultant was a negative 23 kilonewtons. Okay, I'm going to put negative 23 kilonewtons. Okay, units in all phases. So now here we're going to notice top to bottom, we are going to have a cancellation. We're going to have a cancellation of the kilonewtons. So cancel those out. And then because we have two negatives, negative divided by a negative, it becomes a positive, right? Okay. Notice we did not cross out meters. This is why I want you to always put your units in all phases of the problem. If I'm looking for an R bar value, an R bar value is a distance. Does it make sense that meters are not crossed out here? Yes. All right. That gives you your clue that you set this up properly. If you end up with not canceled out units that are appropriate for whatever you are trying to solve for, then you know that there was probably maybe you mixed something up along the way, okay? That's why I am so adamant about units. Statics, strength of materials, machine elements, kinematics. You guys get to do it all the way through, okay? So get used to it now because it's required going forward, okay? All right, so we've got meters. So our R bar, if we take 202 and divide that by 23, what do we get? You get 8.783 meters. Does that sound right? Okay. All right. Now, that's awesome, right? That's awesome. So the problem wanted us to, let's see. The problem said, determine the resultant or equivalent force, okay? And then where it's acting. So we found the resultant right here, right? 23 kilonewtons going down. We found R bar, right? Now we've got to draw our diagram. Okay, now we got to draw our diagram. So, my little straight edge out here. I'm going to draw my A, my C. And you draw the resultant. Give it a shot. Draw the resultant with the information that you got using R bar and R. Draw where you believe the resultant would be, the one force, and where it would be located. Okay, so what you should be finding is that you should find that, remind me, this was 10 meters wide, yeah, long. Your resultant is going to be closer to C this time. Now, in the book, you're going to notice that they use this symbol. It's a cursive E, like an epsilon. And all it means is that's an equivalent force. It's equivalent to the individual forces. Does that make sense, everybody? So it's not an individual concentrated load that we're putting there. This is an equivalent load. This is the resultant, okay?
Right. So that equivalent symbol, is there a specific, should we always put in that like middle of the vector or?
Yep, somewhere like that. That just corresponds to the fact that this is not an applied external load. Does that make sense to everybody? Yeah. Okay, so now what we're going to do is we need to then add in where our R bar is. Our R bar is 8.783 because we summed our moments around point A. Okay, and we use that to calculate this, then this dimension is going to be our R bar, okay? And it's going to be to the location of our resultant. So this is going to be our 8.783, and you can say R bar is equal to, and that's going to be meters, okay? And we probably should put that this is 23 kilonewtons, the resultant. Do not put a negative in front of it at that point. Why don't we want to put a negative on here? The answer came out negative. Yes, Jesse. So remember, the negative says that it's going downward. So when we show our vector with the arrowhead going down, that's what the negative represents. So we could just have to put the actual value here. All right. You have to always show me this final diagram when you're calculating these resultants. It lets me know that you understand what the numbers are that you just calculated, okay? Now, one check that you're going to want to do. Remember when we had our total moment was 102, it was a negative 102. What that negative means is, according to our convention, this is going to have the tendency to rotate in a clockwise direction. So what you want to do is at the very end, and this is not something you have to write out, but take your finger, put it back on A, pull in the direction of your resultant. And is it going in a clockwise direction? It indeed is. So that's just kind of another way for you to confirm that the direction is appropriate and that you put it in the right direction, okay? Or in the right place. All right, questions? All right, resultant of parallel force systems. Let's do another one. This is fun. Okay. Let's turn the page. We are going to go to the problem section. We're going to do problem 4.9 on page 72. Okay. And if you look, page 72, they've got a couple problems here. 4.9 is the one that we're going to be focusing on. So it says here, determine the resultant of the parallel force shown. Okay, force system shown. Locate the resultant with respect to, it says A and D. We're just going to do it with respect to A. We would have to rewrite or redo it in respect to D, so we're fine. All right, so what we're going to do is we're going to draw a line and we're going to do our free body diagram. So that's going to be the first thing along with our convention. Same convention. Okay. And then now we're going to draw a simple horizontal line. And what are the letters? A, B, C, and D. Nice and big. There's no reason to make this small, okay? Use paper, all right? And give me it so that it's way easier for me to read. And when you want to look back at it as well. So point A, then I've got B. Let's see here. 5, here's B. And then C. Here-ish. Okay, and then D. Okay, this is 0.5 meters. This is 0.9 meters. And this is 1.2 meters. And that's distances in between each one of the letters. As we look at the forces, there are 3 forces, 4.8 kilonewtons going down at B. Now you'll notice that 9.6 is up on this, I call it like a little dog leg. That's above there. We are finding the resultant of these 3 forces, this set of parallel forces. So we're going to move that along its line of action, and we're actually going to simulate it at point C. So we're not going to even worry about that dog leg, okay? That it really has no bearing on what we're trying to solve for. And then we're going to have the 14.4 going down at D. Okay. So here. So free body diagram and convention in place. Notice we have each one of our forces and points labeled. We have distances, as they're given to us. They didn't label each one of the forces as F1, F2, F3. Their magnitudes already given to us, so that's fine. You don't have to give them labels. But when we find our resultant, remember that's going to be capital R. Don't use any other variable for resultants, just capital R. So the next step here is to determine our resultant force. So as we look here, we're in the vertical plane, if you would, for all three of those forces. Go ahead and write first the equation to solve for it in variable form, and then solve for your resultant. I'm going to give you a little bit of time to write it down, and then we'll go through it together. We have three parallel forces. They're all in that vertical direction. So we are going to sum our forces in the y direction to get our resultant. Okay, sum the forces equal to the resultant. And you can put ry if you want to. That's totally fine. But it's only going to be in the y direction, so I'm just calling it the resultant. So now on the left-hand side here, I'm going to sum my forces in the y. So using my convention up here, these are force mode, if you would. Up, down is all we're worried about. So we're going to have a negative 4.8 kilonewtons, a positive 9.6, it's going up kilonewtons, and a negative 14.4 kilonewtons. And then that is going to equal our resultant. Okay. So I want to see these with their units and their signs, that's going to equal your resultant, and then we can combine them. What do we get for the magnitude of our resultant? Negative something, huh? Say it again.
Negative 9.
9.34. Did anybody else get that? 9.6. Negative 9.6. Oh, Jacob, maybe check your value. Virtually, did you guys get negative 9.6? That actually looks correct to me. All right. Hopefully you did virtually. Hope you guys are following along. All right. So this is one of our answers. We are trying to find the resultant. We have a negative value that tells us that it's going to be pointing down, and its magnitude is 9.6 kilonewtons. Okay. Now, that's nice. We got to find where it's located. Okay. And so to find where it's located, we need to sum the moments around one of the points. Okay. So notice we're going to determine the moment generated by the original individual forces along that beam. So if we go back up here, probably the logical place to start is we're going to put our finger on A, and we're going to determine what the moments are total of the individuals here. Okay. So go ahead and sum your moment around. I'm going to actually start over to the left because I'm going to have three of them, and I know I write big. So I'm going to sum my moments around point A equal to, and then you're going to start the first one, and you're going to have a plus or minus out front. Okay. And then so on. You're going to have three moments along here. So go ahead and see what you come up with, and then we'll go over it together. Always make sure that when you're doing your moments that you put the parentheses around it so that in the parentheses, you have your force times its perpendicular distance. And then out front of the parentheses is where your sign is going to go, positive or negative. Oh. All right, let's start looking. So I'm going to put my finger on A and I'm going to start where B, the 4.8 is coming down, and it is going to cause a rotation. It's going to be a negatively directed rotation. So I'm going to have a negative out front and the moment is going to be 4.8 kilonewtons times 0.5 meters. So down here, I'm going to put a negative out front, 4.8 kilonewtons times 0.5 millimeters. I'm sorry, meters, not millimeters. Okay, that's my first one. Go back up, put my finger back on A, pull in the direction of the 9.6. It is going to cause a rotation that is counterclockwise. So this one will be positive, right? The direction of rotation. And then the moment is going to be 4.6 kilonewtons times a total distance from A of 1.4 meters. So this is going to be a positive up front because it's counterclockwise. 9.6 kilonewtons times 1.4 meters. And then the last one that we have is going to be the 14.4 that is going to rotate clockwise. 14.4 times, what's my total distance here? 1.2, 1.7, 2.6? Yep. Okay. It's going to be negative 14.4 kilonewtons times 2.6 meters. Okay. Any questions on that? So make sure you write it out for me. Make sure you have parentheses, your units, positives and negatives out front based on the rotation. All right, what is our total moment around A? What do we get? This is what we have in the room. How about virtually? What do you guys have? Negative 26.4 kilonewton meters. I don't know if I have. Yes, Gabrielle got that. Awesome. Just gonna put this up here to make sure I have my thing on.
Yep, that's what I got.
That's what you got too? Awesome. Thank you. Thank you. Thank you. All right. Now we're going to turn our page. So we've got our resultant. We're not going to put a box around our moment. This is the moment that's created by the individual forces. Okay. So now over here, we're going to determine the placement of our resultant. So we need to find R bar. So recalling that equation, we know that R bar is equal to the sum of the moments around point A, because we summed around point A, divided by our resultant. Okay. So this is going to be equal to negative 26.4 kilonewton meters. Okay. Divided by negative 9.6 kilonewtons. Okay. Kilonewtons cancel. Make sure you cancel those. And then top to bottom become positive. So our R bar value, what do we get? 26.4 divided by 9.6.
2.75 meters.
2.75 meters. Everybody should be doing it, right? This is part of our final answer. Make sure you can get the same values. Okay. Now the last step, we have our resultant. We have where it's going to be located. Draw a diagram of what this looks like. Okay. Show R bar, and show any additional information. Okay. Mhm. Now, you'll notice that the length of our part or our beam or our rod is 2.6 meters from A to D. And our R bar is greater than that. So that means that our resultant is actually off of the part, okay? Now you don't have to scale it, but it wouldn't be on the part. It wouldn't be between A and D. It's actually going to be to the right of D. So this is going to be my resultant is equal to 9.6 kilonewtons. And its R bar distance is going to be from A all the way to our resultant. So this is going to be R bar is equal to 2.75 meters. Okay. And that is okay. So don't think, oh, I must have done this wrong. No, sometimes they don't land on the actual part. And that's okay. That's just telling us where we would locate it. Unfortunately, it's not on the part. Okay. Now, where is an instance for example, you might be wondering, when would I ever use this? Okay. I'll give you an example. Let's say you have a beam and it's loaded multiple places and there is too much deflection. You're having an issue with it deflecting too much. Okay. You want to find where is the best place to put a support. So you want to find where is the resultant in relationship to another point so that if I want to prop it up or put a support there, I want to put it wherever it's going to make the most sense. Is that make sense? Like for an application, you know, a practical application of why you would do this. Okay. Okay. So now we've got two examples of finding resultants. Okay. Using or finding resultants that have that are parallel to one another. They don't have intersections. Up to this point, we were looking at concurrent force systems where they share the same point, but now this is parallel force systems. So let's take a peek at our application problems, okay? And what I want to do is I want to look in Module 4, our application problems, and we're going to write down what they are, okay? What are our application problems? So I'm going to click on the PDF that we see here. And the ones that we have at the beginning here, okay, we've got 4.1, 6, 8, 10, 12. Okay. 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 All right. So I want to go back underneath my camera. The four problems that we have at the beginning of this module 4, like up until this point, are these four problems that would be assigned to you in the application problems. What I want to do right now is take a peek at those so that we can kind of, you know, instead of moving forward and adding more to it, let's just kind of review where we're at by making sure we understand what each one of these problems is looking for, and then maybe setting up a couple of these, okay? So let's start by looking at problem 4.1. So problem 4.1 in this handout is going to be found on page, next one. There we go. On page 69. So it's at the bottom of the first column that we see here. So it's right down here. And it says we want to determine the moment of the forces about points A, B, C, and D for the beam shown. Okay. So in this case, let's see how we would set that up. So we're going to use this illustration 4.1. Problem 4.1. Okay. I am starting a new rule when you hand your stuff in. One problem per page. All right. I don't want to see multiple problems on pages anymore. Start a new page, start a new problem, and work down. Okay. Just easier for me. You're doing me a favor. I'm gonna just kind of make it the way I want it. Yeah, I just find that when people do start on a new problem, it just makes it easier to kind of see what's there. All right. Now what I'm going to do is before I even start drawing my free body diagram, I'm going to put my convention on because I don't want to forget that because that's otherwise it's going to be points off. Then I'm going to do my free body diagram and I'm going to draw a line, simple line, A to D, and then we're going to be putting the points in between. Okay. And I'm going to make this again, like the top half of my page. This is going to be A. This is going to be D. And then we are going to put the points in between. So looks like here I've got 8. I'm just going to try to proportionally put these on here. I'm not going to scale it, but this is going to be 12 kilonewtons. This is point B. This is going to be 8 kilonewtons. This is not a point, but it's 4 meters between, 4 meters between. And then there's going to be a point C right here. This is 2 meters between. Should have put them all in the bottom. You know what I'll do? Go like this. That's why we have pencils. This is point B, this is point C. I'm going to put 2 meters here. That looks better. And then 5 meters here. And then at point D, we've got 10 kilonewtons going up. So here's my free body diagram of what I have here. And the problem asks me, or tells us that they want to know what the moments are about points A, B, C, and D. Yes, okay. So we're going to then do sum the moments around A, values, sum the moments around B and C. So let's do the first one together, just so you have a good idea of what's expected. So free body diagram. So the first part here is going to be sum the moment around A is equal to. Okay, so it wants to know what the moment is. So it's not equal to a resultant or anything like that. It just wants to know what is the moment about A. So I'm going to put my finger on A. I'm going to rotate in the direction of the first offset force. So this is going to be 8 kilonewtons times perpendicular distance, 4 meters. And it is going to rotate in a counterclockwise direction, so positive out front. The next moment is going to be 12 kilonewtons times 8 meters, and it is going to rotate clockwise, so negative out front. And then lastly, we have the 10 kilonewtons. So parentheses, 10 kilonewtons times all the way from A. Oh my goodness. 9, 11, 16. Is that the number? Okay, just so you, is it 15? Wait.
Right?
Yes, it is 15. See? Just so you know, I suck in my head. All right. But I always try. I always try. And then before I did get it right. So then I think, all right, cool. I'm on a roll. And then brings it back to reality. I can't do it. Very calculator dependent. Okay. Sign out front of this one is going to be positive. Okay. So now we want to multiply, add, subtract, and then we're going to have a total moment around A. And what do you get? 86 kilonewton meters. Anybody else get that value, positive value? Okay. So now you're just going to put a box around this because this is one of your final answers. Okay. Because that's what it's looking for. What is the moment around A? Now you're going to continue. You're going to put your finger on B, C, and then D, and then you'll finish up the problem. Okay. So don't start another problem on this page. You're going to finish it up going down below. All right. Any questions on 4.1? That's your first, if you would, application problem for that section. Okay. Our next application problem is 4.6, which I think is in the same area. So I think it's going to be on the second page here. Yes, it is. On page 70 in our handout, up in the upper right-hand corner, is the illustration for 4.6. Its problem statement is down at the bottom here of the first column, okay? So it wants us to determine the moment of the force shown about points P, Q, R, and S, okay? So P, Q, R, and S are in that illustration. So P, Q, R, and S. Now, as you can see here, for this problem, you have forces that are not horizontal or vertical. So you get to do the components of this force, right, at Q and the components at R. So again, why don't we go through the process of setting up our free body diagram, making sure we've got it right, and doing one of the some of the moments around one of the points, okay, to kind of get you kicked off. So go ahead and draw your free body diagram. I'll keep this up here so that just in case you don't have the PDF, oopsie, the PDF printed out, you can use this as your illustration. And then we will compare. So this is 4.6. Okay. Yeah. You should get something that looks similar to what I have up here. This is point P. We're going to have an X and Y at Q and an X and Y at R. We do need to calculate, I'm calling this angle alpha, okay? We do need to calculate that based on the information they give us on the slope of that line, okay? So to calculate this alpha, okay, if we look at the example, it says that it has a rise of 3.5 over a run of 4. So if we want this angle, we would do the tangent of alpha is equal to the side opposite over the adjacent. So this would be tan alpha is equal to side opposite, which was 3.5. And it's just units. They're not giving us, it's just giving us units. So you don't have to put any units in back, sorry, any units in back of it. And then it's going to be 4 here because it could be 4 feet. It could be 3.5 inches. It could be millimeters, whatever. So alpha then, what do we get for our angle?
1.18 degrees.
Yes, 41.18, did you say?
Yep.
Yes. Okay, so that's going to be the angle then that we use for the components at Q. We were given the angle of 40 degrees at R. So now what you want to do is you want to calculate down below your X and Y components for R and Q. Okay, so I'll do mine. You guys can work yours as well and then take a peek to see how you're doing. Okay. Okay, so you should have components for your X and Y's of Q and R for each one. Okay, just double check your values here to be sure that they match what I have. Did everybody get the same thing, hopefully? Okay. I didn't double check mine, but I'm pretty confident. Okay. All right, once that we have this, remember, once we have them in the X and Y axes, now the reason we did that is so we can easily get the perpendicular distances rather than having to calculate them, okay? So it's calculating one or the other, and usually the components is just a little bit easier, okay? Not as much construction, if you would. So now what this problem asked us to do, we look at the bottom here, says determine the moment of the forces about P, Q, R, and S, okay? So we'll do one of them, okay, to be sure you're on the right track. So which one do we want to do? P, Q, R, or S? P, Q, R, and S. What point? Ready? Let's do P. Okay, I like it. So that means we're going to put our finger up on P here, right? So what I'm going to do is, looks like there's going to be quite a few forces. So I'm going to sum my moment around point P, not B, P, equal to, okay? So clearly label that. Tell me what you're going to do. We're going to put our finger on P. So what's nice about that is it takes out one of the forces, right? So it's not, we're not going to include the 800. I'm going to go over to Q first. All right. So I'm going to notice that we have our Y component here. Our Y, if we rotate, when we put our finger on P, it's going to cause a rotation. So it is offset, causing a moment. It's going to rotate in a counterclockwise direction. So that means it's going to be positive out front. The magnitude of our QY is 658.4, and its perpendicular distance, you see from P, is 72 inches. Okay. So in parentheses, we're going to do 658.4 pounds. Make sure you put your units there, times 72 inches. You can use the little, you know, two little front, or I don't know what they're called, quotes. And then we want to put a positive out front because it's a counterclockwise direction of rotation. Going back up, P. We're going to pull in the direction of QX, okay? It causes rotation, okay? And it looks, and it's creating a counterclockwise, so that'll be positive again. So I'm going to put positive out front. My QX is 752.6 pounds. Make sure you put the units in there either by symbol or LB, times perpendicular distance. Our P is here. Remember, we can move this force anywhere along its line of action. It'll have the same net effect on the body. So if I pull my Q back, you see the distance is 24 inches. Okay, 24 inches. The next one, let's go down to R. RY. RY does not cause rotation. It pushes right through that point. It would have a distance of 0, so we don't include it. But we do have an RX causing a rotation, okay? And that's going to be positive as well because it's going counterclockwise. So I'm going to put a positive out front. Our RX is 1,149.1 pounds. If you left it at 149 or 1,149, you're fine, okay? 0.1 is probably a little bit of overkill when we're talking thousands of pounds. And then our perpendicular distance from P all the way down to RX is going to be 24 plus 48. Is that 72? I think so. Thank you. See, I'm back. I got that one right. All right, now you're simply going to multiply and add these three together. What do you get for a moment about P? And we got to give Nick a break. Tyler, what did you get?
148,205 foot-pound inches, foot inches.
Tell me again. 148, then what?
205 foot inches.
We're going to do pound inches. Pound inches, not
Oh.
foot inches. Yep, that's okay. I know,
Yeah, yeah,
I know. You can do this, usually in my final answer, I'll do pound and then inches. I usually write it out. In here, I usually do the symbol only because usually I need the room. That's it. But as long as you do it, you can do it either way. There we go. Anybody else get that same number confirmed? Okay, awesome. So that's one of the 4. So you have 3 more to do here for this problem. Okay? For that, we're getting started on your homework already, but you can't wait to continue on. I don't blame you. Looks fun. You get to do this homework. That's what's awesome. All right. We got 2 more problems let's look at. We've got 8 and 10. That's going to be in our next section. So I'm going to put this over here. So again, these problems, I think I put the page number for each one of them. We're going to go a couple pages ahead, back to page 72. And you're going to be doing number 8. And then the other one's going to be number 10, which is up on the top. So let's look at number 8 here. Okay. Number 8, it says for the wheel loads shown, determine the resultant and locate the resultant with respect to A and B. Just do it in respect to A. It's going to be, somewhere between the two, I think. All right. So go ahead and draw your convention and your free body diagram. I got to grab a piece of paper. Okay. For this problem, I'll kind of put it here again. If you don't have this printed out, this way you can see the values. We're going to draw this as a line through A. We're not even going to worry about that those are wheels. We're just going to draw a straight line from A to B and then put all of the forces respectively along that line. So starting again with a brand new piece because you're going to be adding to the other ones. So you want to make sure you have enough room to do that. So you should have a diagram that looks similar to this. So this is your free body diagram. 0.5 kips for the first 3 forces, and then 1.5 kips for the last force that's at B. All of them are going down. Now, if you need to look back at the process, this is the stuff we've been looking at today. So we want to find the resultant of those 4 forces, and we want to place it along line A to B to have the same net effect on the body, right? So if we go back to page 11 in our handout, at the bottom here, free body diagram and convention, and then I'll take my little check marks off here. Then we're going to determine the resultant by summing the forces in the direction that they are found. So what direction are these forces found in?
The Y direction.
The Y direction, right? They're vertical, okay? So that means that we are going to sum our forces in the Y direction to get our resultant, okay? Remember, they're parallel, they're non-intersecting, so that it's going to lie along that vertical, line or axis. So now we're on the left-hand side of our equation, we're going to sum. So we're going to do a negative 0.5 kips, negative 0.5 kips, negative 0.5 kips, negative 1.5 kips. Okay, and that's summing our forces in the Y equal to our resultant. And then now we can add them together. So we've got 1.5, 2, 2.5, 3.5. No, 2.5. 1, 2, 2, no, 3, right?
Mhm.
Yeah. Negative 3 kips is equal to our resultant. Box around that because that's the magnitude of our resultant. Okay. We want to number the steps. Number one would be our free body diagram. Okay. And convention. Number two is going to be resultant. Okay. Then step number three, if we go back to our process, determine the moment generated by the original individual forces. So now we want to sum our moments, okay? Wants to know what the moment is or what the placement of this resultant is in respect to points A and B. Now, A and B lie along the same line. We can just sum our moments around A, okay? And again, I'm picking it just because it's on the left-hand side. So A is going to be equal to. So now we put our finger at A. The first 1.5 is going through it, so we don't include it in the moment equation, but the second 1.5 is going to cause a rotation, right? So go ahead and write the moment for each one of these. And you can go ahead and continue. Oh, I'm putting. You should get a negatively directed moment for each one of those. Everybody should be calculating the answer. Virtually, I'm going to look for somebody virtually to come up, tell me what some of your moments around A was for your problem.
-18 kip pound or kip feet.
Kip feet, yes, 18, but is there a sign associated with that?
Negative.
Negative, exactly. -18 kip feet. Yep. Is that what you got?
I
Confirmed?
got -24.
Oh, we've got a 20.
I also got
24. Okay,
-24.
that's
No,
what I'm confirming.
I got that as well. I'm sorry. I looked at
Oh,
the.
that's okay.
I'm.
It
I'm
happens.
sorry.
Calculate. We got thick fingers sometimes. That's okay. Yep. Okay. -24. I don't have the answer key in front of me, so I'm trusting you guys. I didn't get a chance to plug it in. All right. So that is your moment around point A. Oh, actually, this is not, I'm so sorry. This is not one of them, is it? That's not an answer. We're looking for now the placement, okay? So now we've got our total moment based on the individual forces. Now we want to determine the placement. So we need to find R bar, right? So go ahead and write the equation for R bar. So R bar is equal to, if you have to look back in your handout, that's okay. Yes, it's going to be the sum of the moment around A. Remember, it's the moment that we just found that we had here. Sometimes it might be a different letter, okay? It's just been A's, I think, for all of them that we've done so far. And then we're going to divide that by our resultant. Good, 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 good. And then we're going to put those values in there, -24 kip feet divided by -3 kips, which was our resultant up on the top. Kips cancel, positives become, or the negatives become positives, and our R bar equals 24 divided by 3. I think that's 8, isn't it? 8 feet. This would have a box around it. That would have a box around it because that's a final answer. So if we go back to our procedure, we have a step 5. We got to draw a final diagram showing the resultant and the R bar with relationship to the points that we just did. So go ahead and draw a final diagram. You have to do this. Required. So make sure you draw a final diagram so that I can look at the answers that you got and you're telling me what they mean, basically. Okay? Any questions on 4.8? We actually did the whole problem. Got a homework problem done, guys. You have to hand this in, okay? You got a homework problem done. All right, let's take a peek at 4.10. I don't think I'm going to do that one. I think I'm going to let you guys do that one independently, but let's make sure you have a good idea of what's required here. So on that same page, 4.10 is right here, and then the illustration is up here. All right. So it says we have a pin connected truss is acted on by the forces as shown, determine the resultant and locate with respect to points A and B. Now, here's the deal. Don't worry, we'll get to do trusses. I think it's module 6. We get to do trusses, but there's more information here than what you really need. I'm going to show you this. Look at this. This is how you're going to draw this. A to B, and it's just going to be a straight line, and you're going to show the 3 forces going down. Don't even put anything about the truss above. Does that make sense? You just want to know what is the resultant of those 3 forces and where is it going to be located with respect to probably A. Okay. So that's what you want to do. Don't worry about the truss members above. They have nothing to do with this problem in trying to find the resultants. Okay. So that's problem 4.10. And I think now you've gotten 3 good examples, including one for homework. Make sure that you hand that in. And then this one's going to reflect that. Yes, Tyler.
I have a question. For the resultant R and R bar diagrams, do we need to put the convention on there?
You did the convention already at the top of your problem. So that is going to go for the entire problem. Yeah.
Okay.
Yeah. So you don't have to redo it. Just once on each one of our problems. Okay. So I am going to stop there our recording and we'll take a break.